Good. We still have 1 minute. still people coming. All right, let me gradually start. It's my great pleasure to introduce Dr. Boran Han from AWS AI. So right now, Boran is a research scientist at AWS, and she got his PhD from Harvard University, physics, right?
Yeah, physics.
So Boran has worked on a lot of topics, from foundations of machine learning and deep learning to some very hardcore and very physical science topics like machine learning for microscopy. So actually some folks in my group are also work on that. And since moved to AWS AI, Boran has focused mostly on AI for science. Especially recently, he's been working on multimodal foundational models. Problems like how to improve the accuracy and how to improve the trustworthiness. And of course, she's devote her energy mostly to scientific problems. She's trying to build a foundation model for remote sensing, right? Yes. All right, it's your floor. Thank you.
Okay, so thank you, Chi, for inviting me here. So I guess as what you introduced, I have a very broad interest, but in terms of the time sake, I will only talk about 2 topics within this 1 hour, which is the multimodal LLM, and the other one is the AI for science, which is its application in the geospatial domain. So now we are living in the age of foundation model. So foundation model is trained with a large number of the data, and that's what we call the pre-training. And then we can adapt it to downstream tests, like various different downstream tests. So the foundational model, because it's trained from the large data, so it can adapt to a large range of downstream tests. And the technique can be used for such as fine-tuning or in-context learning. So here, building of efficient foundation model is very important since we will bring the foundation model to a broader community. So specifically for this talk, we try to answer 4 questions. So how to leverage the retrieved information for in-context example to improve multimodal LLM performance. And the next one is how to leverage the existing foundation model for domain-specific pre-training. And the next one is how to transfer multiple foundation model into one small model so that we can do an efficient deployment. And then the next one is how can generative AI benefit daily life? So I will use the weather forecast as an example. For the time sake, the last topic will probably I will briefly talk about it. So as I mentioned, foundation model are usually very large. So which means that fine-tuning the foundation model can be really challenging as well. So one way that we can get around it is by the in-context learning. So this is a known method for the large language model. So when the model is large enough, then there will be an emergent skill that whenever we put more in-context example in it, the large language model can magically give the answer for that example. So to be more specific, how the in-context learning work is we will provide several examples with the annotation pair, and then we also put the query sample. So the query sample, after it goes through the LLM, then it will be able to give the answer even if the LLM is not fine-tuned or pre-trained with that specific test. And the image and the image, the example and the label pair are usually called the support set. And the one that we want to get the answer is called the query set. So, however, as I mentioned, that LLM is the emergent skill for in-context learning is the emergent skill for the LLM. So it remains a little bit unknown how can we adapt it to the multimodal front, and is it possible to also adapt it to small multimodal unified model as well. So that's why, as a warm-up, we try to propose a new method, which is called mixed. So the mix is a light-weighted embedding network that can prepend before any multi-model unified model, and then it is able to do the in-context learning. So the way how it works is we try for the multi-model unified model, we try to freeze it, and then we do instruction fine-tuning. So during the instruction fine-tuning, we have the pre-training from different tests, such as image captioning, visual grounding, VQA, and object detection, or the mask image modeling. So we try to add, for the fine-tuning, instruction fine-tuning, we will only fine-tune the mix part and then freeze the multi-model unified model. And we test our model on the encoder decoder model, such as OFA, and also the decoder only model, such as Lava. And to be more specific, how it works is for the support set, because we are dealing with the multi-model front. So for each sequence of the support set, it will comprise of 3 parts, which is the image, instruction, and the target. So that's why we call it the instruction fine-tuning. So it could have a multiple set. And during our experiment, we find that having 2 shots or 3 shots will give a good performance. And even only instruction fine-tuning for a few epochs can give a very good result and enable the in-context learning capability for relatively small multi-model unified model. And here shows the example where we have a support set of question answering. For example, what does this image describe? And the next one is the object detection. What region does the text dog describe? So then for the query set, it's all going into the training. And then it's relatively compute efficient, as here we show the result. If you take a look at the 3 panel on the left, so we try to benchmark our data sets through different tests, such as question answering, captioning, and also the visual grounding. The x-axis is the model size. So our model is on the very left, so which indicate that our model is relatively small, and the y-axis describe the metric, and we usually have a very high performance. So you can see that it outbeat for the in-context capability, it outbeat the model that's at 3 billion to 9 billion, and it's also very comparable to other model like the MMICL, which is an 11 billion model. So, and the other thing we also want to test is whether we do an instruction fine-tuning, is it possible to adapt to unlock the capability for the unknown test. So that's why we also tested the Flickr 30K. So that's the one on the corner. So that's the one on the corner. And then we also tested like OKVQA. So that's the test that we haven't put into the instruction fine-tuning. We are able to see that through this like a small embedding network, it is able to unlock the in-context learning capability. I also showcase some example on the right side. So for example, for the small object, we are actually having a better accuracy than other models, such as the Unified I/O. And the other thing is, if it is possible to apply it to a relatively large network, so a large model such as the Lava 7B. So we prepend the same technology to the Lava 7B, and we find that compared with the original vanilla 7B Lava, our result does show a better accuracy. So that's so that's just a warm up for the talk, and then however, this work is a little bit preliminary, because as we haven't solved several questions, which is how to select the in-context example, right? So we just manually for this paper, we just randomly select the in-context example here. So how do we select the in-context example? And here we only do fine-tune the small embedding before the multi-model unified model. Then how do we smartly integrate the relevant in-context example into our model that is a little bit unknown? So that's why we
hi, Brian.
Yeah.
Can I ask some clarification questions?
Yeah.
Yeah, so if you go back to the 2 slides earlier,
Mhm.
Can you explain a little bit more on the difference between the support samples and query samples? I noticed that from the architecture, you concatenate them.
Mhm.
But is there any, can you explain a little bit more what is the meaning of support samples here?
Okay, yeah, sure. So I think not sure if you hear the question, so I can rephrase the question a little bit. So the question is, what's the difference between support sample and the query sample? So the support sample meaning that for the in-context learning, we need to provide the label for that sample as well. For the query sample, although this slide is a little bit confusing, we do have, because this is the instruction fine-tuning, so we do have the label, but that will be training during the fine-tuning stage, instruction fine-tuning stage. So that won't be the target for the query sample won't be input as a prompt into the LLM. So that will be the difference. So the support set will have the label import into the LLM, but for the queries data, we don't have the label input into the LLM. Instead, we have it as an output.
Got it. So the support samples are like prepended to the queries in the context of in-context learning.
Right.
And during the test, do you maintain the same format as the tuning stage? So you prepend the same number of support samples?
Right. So I think that's a very good good question. So for this, so the question was asked is for the test set for the inference time, do we still need to prepend the support set? So like we tested in both cases. So the one that we show is the one that we prepend with the support set. However, if we don't prepend it, it still shows some improvement. But for it to reach the maximum accuracy, we usually need to, for the inference time, we also need to prepend the support set as well.
Okay, and in prepending that support samples, do we need to try different, a diverse set of modalities?
For different set of modality, so you mean like so far we are dealing with the text image. So are you including audio, video, or something?
Maybe I should say different task types. So here in your examples, you have question and answer, and also the coordinates as the answer, right? So we have both text and coordinates. And so do you try to cover all the types of tokens?
Right. Yeah. So I think for the support set, we will try to include as many tests as possible.
Okay. Okay, thanks.
So I hope that I answer your question. So for the next one is to try to optimize the in-context example. So here we are getting inspired by the retrieval augmented generation. So which means that we use a small retrieval to retrieve the one that's very similar to the query data. And the goal is very simple. We just want to achieve a better performance of course. And then the second one is whether we can broaden it. For example, if there are some domain specific question, if we provide more, like that will require a more intensive knowledge. So if we have a RAG that's encrypting it, is it possible to answer any scientific question? And the next one is like there are some, for example, although we are still dealing with the text image modality, but within the image modality, there will be also within different form, like a sequence of the image. Is it able to answer the sequence of the image? So that's the three goals we want to solve for the next few following slide. So just to give a little bit of overview, so we design a hierarchy architecture that will integrate the retrieved example. And our method, as the title indicated, is also very lightweighted. So this talk is about the efficiency. So it's very lightweighted, and it also can be applied to process long multimodal context example. And then we also achieve the state-of-the-art performance. So we outperformed Lava with this module integrated. So here is the diagram showing how it will work. So as I said, we get inspired by the RAG itself. So let's go over one by one. So first, we have a question. Say, for example, it's from a science QA question. What two magnets are placed as shown? shown, will these magnets attract or repel each other? So you can see that the image is very important to answer this question. So that's why it provides a reason why we are developing a multimodal LLM. And then we have the image and text pair, right? So we go through a camel retrieval. So this retrieval can be replaced by all kinds of embedding model, like embedding foundation model, such as image bind. So far we are using the image bind, so which means that we can easily upscale it to audio and video as well, since they are pre-trained with the audio and the video. However, we are focusing on the text and image. So after going into the data store, we will have an image and text pair. So for the image and text pair, it will go through a hierarchical structure called camel perceiver. So within the camel perceiver, we design a language perceiver and vision perceiver. So after we get the token from the word, so we will have a text embedding, and the text embedding will go through a self-attention that's within the language perceiver, and then it will cross-attend the image embedding, and well, the image embedding is obtained from the pre-trained VIT. So all these are, so for the embedding model, this time is frozen. So we only need to fine-tune the language perceiver, vision perceiver, and also the context perceiver. So now we get the embedding from the language perceiver and the image perceiver. What we need to do is we will need to cross-attend a learnable query from the context perceiver. So this is a learnable query. So we get that idea from Q-former, which is a popular scheme for the BLIP2. So I'm not sure whether you heard of it, but however, our is more efficient, since for the BLIP2, we will require more layer, but for us, like we only require 2 or 3 layers, that could be enough. And we think that having the language perceiver and the vision perceiver will help in each case, because we have a language expert and a vision expert to deal with the situation in each case. And then we still are putting this situation in the in-context learning. So we have a query queue, and then we just prepend the context before the query queue, and then it will go through our LLM. So the LLM is a pre-trained one. So this one here, we use Lava as a pre-trained one. So we find that it does show a better accuracy. So we do a fine-tuning on the science QA. Like science QA is a high school or college level science question, which comprise of physics, earth science, like everything biology together, and then compare with, so we evaluate its reasoning capability, and we find that it have a greater performance than the MMCOT, which is also a few shot learning method. And of course, we are better than the Lava 7B because we incorporate more relevant context. But in the future, like in the following slide, we will compare with the one with the like a few shots together. But as you can tell that we are better than the GPT-4 COT and GPT-3 COT, and also other like a human average as well. So we, as we what a paper normally do, so we just benchmark with small data set. We do a multi-test learning as well. So the multi-test learning we do contains about 600K image data pair from all kinds of tests. It's similar as the mix as I presented before. So the camel does show a better performance compared with BLIP, which is 13B, and we have 2 models. One is 7B and one is the 13B. And then it's also better than the Queen and also Lava as well. So, and then
one of our pre-correction here. So when you do the comparison, do we take into account the different amount of training data used and also the model size?
Oh, right. So that's a very good question. So that's why we mark the model size Lava 7B and 13B together. But so we did. So I know that it's a little bit unfair, but we try to bring it to the similar scale as other model. And what was the next question?
The different amount of training data, because I suppose different companies probably have.
Right. Yes, that's a very good question. So we cannot compare, we cannot for sure that we have the same amount of the data as them, but our pre-training data is similar as Lava. So we are comparing with the similar pre-training data. So for the Lava, it's a fair comparison, but for other data set, it's almost impossible to have a really fair comparison. So I think that so that's also a problem for the MLM research, like because every people have their own pre-training data, and because our method is inspired by RAG, right? So it's unfair to just compare with any model without RAG. So that's why we compare.
Sorry to interrupt. I guess another question is that what amount of human feedback they get, right? That's probably another important question. Right?
Right. So for you mean RLHF?
I mean, when I say training data, I really mean the static training data. But when I say the human feedback, I mean when you specialized to the Q&A kind of task. I know that every of the foundation models or the foundation conversation models at least are using human in the loop kind of design, right? They got a lot of human feedback. Sometimes human will directly write something for them, right? So this part is also unknown, right? When we do the comparison.
Oh, right.
Yes, okay.
Yeah, so unfortunately, this part is also unknown. Right, so and
Boran, can I ask a clarification? So
okay.
previously we were talking about the in-context learning, but here my understanding is that we actually fine-tune it. Is that right?
Right. So I think we did fine tune it, but the thing is we only fine tune the vision perceiver and the vision perceiver, language perceiver, and the context perceiver.
Oh, so we don't fine tune a specific task.
Right. It won't fine tune on a specific task. It will fine tune on just like a multi-task learning.
Okay. And when we evaluate, we still evaluate on some unseen task. Is that right?
Right. Yeah. So we will evaluate on some unseen task.
Okay. And when we evaluate, do people generally consider generative quality rather than only the downstream tasks? Also the just language modeling quality.
So I think the generation quality is a really good question. So the question that's being asked, like when we do the evaluation, do we need to evaluate the generative quality? So for our samples, for the downstream type, for the VQA question, some of them are just like a multi-task, multi-choice question. So it does have or it have a numerical answer at the end. So it's easier to do an evaluation if we just compare with the final answer.
Okay. But do people use something like perplexity to evaluate in general?
Sorry, what was that question?
Use some metric like perplexity to evaluate.
I think not that I know of.
Okay, I see. Thank you.
Okay. So and then here we show the result with the RAG together. So the RAG is the one. So there are several RAG paper that called CM3. That's one of the high profile paper on ICML. And then we do show that even with the model that's equipped with RAG, we are having a better accuracy. And then we also compare with other video shot and few shot models such as Flamingo, MMICL. It's the same comparison as the paper that I talked before. And we said like it does outperform. And then we also compare with did some ablation study to show that our model is really efficient compared with the original Q form, that it doesn't require a lot of layer, and few shot is good enough. Like increasing the shot doesn't increase the accuracy too much. And then our running time is also very short, so that just showcase how efficient our work is. And here shows some case study, which is the highlight. So what we have is like, if you remember, the goal of our model is to provide more accurate information about some domain-specific knowledge. For example, for the first one, what is the name of the architecture? And the Lava 1.5 give the result saying it's a castle. And then if we have retrieved with the context information, it's a Great Wall of China, then the Camel is able to understand with a more accurate answer. Although castle could be accurate, depends on the definition of what castle is. And the next question is we give how to describe it in the scientific view. So it's a development of a butterfly, and then for the context example, we give them a development of a beetle and a frog. So they are having a similar development stage, and then we asked Lava and also Camel to answer the question, and Lava failed to answer it, saying that the caterpillar is the third stage, however, it's the second stage. And then, as I mentioned before, that it's also important to know if we can answer the modality within the image. However, in different format is the sequence of the image. So we give them a scene from Simpson, like the Simpson is walking into the bush. So all the model are giving the correct answer, including GPT-4V. But if we give the same sequence of the image to but reverse wise, then we find that the only Camel is able to give the answer because it takes the first three image as a context. So, but however, even for the GPT-4V, it's not able to answer it. And then for the magic for the RAC is because for the LM, it's difficult. It's pre-trained before a certain time. So it's not very timely manner. So it doesn't reflect the information right now. So that's why we give another test we have is does Macy win the 2023 Ball Oli Dior? Answer the question in short answer. GPT-4V saying that it is unable to do a real-time update, and the Lava just have so it's having a hallucination, and then Camel is able to give the correct answer. And here is also a famous meme, like in the computer vision domain, the Chihuahua versus Muffin. And then so there was also one paper, actually, the reason prompt us to support us to test it is because there was another blog saying like GPT-4V is confused again when you put them into a panel. So that's why we put them into a panel, like with all the image together, and like just as what the blog say, like GPT-4V is confused again. So here's just some more example about so generating a more accurate test. So the next thing we do is we try to give them try to have a prompt saying describe please generate a detailed description for Shanghai city in cyberpunk style. So you can see that with Llama, with Camel, we have a more accurate test, and then when it goes through the DALL-E with the Camel test, it is able to resemble the one that the Shanghai was originally had, but just having in the cyberpunk style. And then for the question itself, it's not able to do that. So that also happened to other example about generating Shanghai in the 19th century as well. So that just concludes my talk for the Camel. So this is the work that we just released it online 1 month ago, and then we are still on the legal process about releasing the pre-trained weight, so that it will be released on the Amazon Science. So that's all for this part. So the next part I'm gonna talk about is the domain-specific pre-training, the GFM. So the next question I'm gonna answer is, let's say we have the domain gap is too big, like the RAG cannot solve it. So for example, for the geospatial domain, it has a multiple sensor. So it's really difficult to do it in the RAG way, although we are testing on that front. And then we just wonder if we hypothetically want to do a pre-training, is it possible to do it in the more efficient way? So we pick the geospatial as a very important example because it is used to understand the Earth better. And through our investigation, we find that we are able to come up with a small amount of the pre-training data. And also we come up with a multi-objective continuous pre-training paradigm. And it is able to adapt to the in-domain knowledge, leveraging existing foundation model. So our GFM have a strong performance and can set on the broader test as what the foundation model is required for. And then as I just briefly said, we come up with a GLPAL. So the GLPAL is made of open source data set with different ground sample. So distant has various class, label and unlabeled. So it has 600K in total. It is relatively small compared with all the other foundation model that like for example, pre-trained with ImageNet or say NLP from like trained with the whole internet. And we surprisingly found that it does work better than just having the Sentinel-2 as the pre-training data set, because we try to calculate the entropy for each image. And for the ImageNet, we find that for the Sentinel-2, it doesn't have enough feature within each image. So that's why having the same amount of the pre-training doesn't really help. And our GLPAL data set is very similar with the ImageNet, and it does it has a higher entropy of that image. And then the next thing we have is to do a pre-training itself. So for the pre-training, we use the mask image modeling. It is a very popular way to do a pre-training, both in the image and in the NLP front. So what we did is we mask some of the patches, and then it goes through an encoder, which is the GFM encoder, and then go through a very light decoder and try to reconstruct the mask patch. So that's what the original mask image modeling is. However, pre-training from scratch really require a lot of compute resource. So we try to leverage the pre-train encoder that's pre-trained from ImageNet 22K. So instead of only having a mask image lost, so we will also have a feature distillation loss, where we extract the intermediate feature from our GFM encoder, and then it got projected with a linear projector, and then it will try to compare the cosine similarity between the pre-trained ImageNet encoder and our GFM intermediate encoder. It found that it does perform very well. So we added the mask image loss together with the cosine similarity lost from both sides. So we test our downstream tests on change detection, classification, multi-label classification, super resolution. So change detection is a special downstream test that's only almost arguably exists in the geospatial domain. So we try to visualize it, compare with the ImageNet random initialization. Our GFM does shows a better result. And remarkably, for the CO2 for the pre-training, how many CO2 is emitted, because we are trying to build a geospatial foundation model. We don't want to emit too much carbon to violate our ideology. So we try to measure the CO2 emission. It does show that it's 20-ish for efficient compared with training from scratch. So this is the 800 epoch training from scratch, and it's also have a better accuracy than the.
So this one, I'm just curious, how people measure this?
We
amount of electricity they use or what?
That's a really good question. So there is a open source online package on how to measure it. I don't know the details. So you just run that package. So during the pre-training, and it is able to calculate. So I can try to Google and then send it to you if you are interested in it. Yeah. So
you kind of electricity and water electricity versus solar.
Okay.
So it's different,
Right, right. So yeah, I'll give my honest answer. I don't know. So you probably is the expert that you can like submit some issue to that GitHub, saying that this is not accurate enough. So actually when we submitted to ICCV, that was a question from a reviewer too. So like it's not accurate. So I think that so I think that's pretty much for the GFM. So by the way, we do have a follow-up work which is pretrained with the multi-sensor GFM, and then when I fly here, I got the news that we got like accepted by CVPR. So for this example, we are only pre-training with the RGB, but we know that for the geospatial, it's beyond just RGB channel. So for example, SAR, like radar image, is very important that it can penetrate the cloud. So we are having another pre-trained model that's pre-trained on multi-sensor. So we hope just the legal process could be faster so that we can release the pre-trained wavelet model. But for this one, you can find the pre-trained model that you can download it and play around with it. So that's it. That's all for the GFM, and then so let's step back a little bit to take a look at this famous foundation model. So we are mostly targeting on the problem about pre-training and also the instruction fine-tuning, like the multitask learning, to release another foundation model. So now let's focus on the downstream test a little bit about the transfer learning itself. So how can we transfer it to different model, and how can we transfer it to small model? So as most of the effort for any institute or like a big tech company, they were mostly focusing on the large scale model, like trying to scale it large and then release the foundation model so that it can break the internet. Then there are very little effort making on improving the technology for the transfer learning itself. So there are several drawbacks for the current transfer learning paradigm. So the current transfer learning just work as we load the pre-trained weight and then followed by the fine-tuning. But however, it will require the pre-trained model and the downstream model to have the identical architecture. However, during the real life like practice, saying it's not very ideal, because when we deal with the customer, sometimes they are on the edge device, right? So it's difficult to deploy, like say, a 400 billion model onto an edge device, and then usually only one single pre-trained model is being used. So although there are some work about like knowledge distillation, trying to distill from different foundation model, but they are just focusing only on one aspect. For example, distilling to a small model under a same test. So here, what we are doing is just to make a clarification. So we are doing a knowledge distillation and the transfer learning at the same time. So we do want to distill it to a small model, but we also want to adapt it to a new test as well. So now, like as I mentioned, for the current paradigm, it's prohibit us from transferring across architecture or transferring from large model to small model efficiently, since it's cross architecture. And the next one is how to transfer multiple model together. So I think we are seriously underutilizing the diversity range of the pre-trained model, as they has been releasing like day and day. So our goal is very simple. So we want to give the transfer learning maximum flexibility. So transfer from any collection of the model of arbitrary size and architecture. So in summarize, to differentiate ourselves from knowledge distillation, we are similar. So we just want to do a distill and transfer in one step, both distill to a small model and transfer to a new test. So while being compute efficient, we want the minimum overhead compared with just training the downstream tasks, like to do a traditional transfer learning, and no fine tuning for the pre-trained model. So we won't fine tune on the pre-trained model itself, and not running on the pre-trained model on the inference time, because if the model is is large enough, inference will be very costly as well. So we also want to be scalable to as many pretrain weight as possible. So just to we have some hypothesis to make it work. So just before I just introduce our design, I just want to go through the notation where we have the downstream feature. So downstream test is the one that we want to optimize. So that's why it's prioritized with theta, with phi. And then we also have the pretrain feature, which can be calculated by a single run of inference, which we call it psi. And then our goal is to leverage the foundation model during the transfer learning. So we try to incentivize the downstream feature to prioritize using the information from psi, which is the information that we get from the foundation model. And then we do want to minimizing the new information so that we can train it faster. So that's why we want to minimize the mutual information with X on condition with psi together. So it's trying to minimizing this small region. So just for the people online, so we are just trying to minimizing this small region over here. And then it could naturally expand it to multiple pretrain model as well, since for the psi, we can just pre-calculate it through a one-time inference time to get all the pretrain weight and then concatenate them together. So we just did some derivation according to some theorem in the mutual information. So adding the mutual information for this overlapping region is the similar. It's equivalent as getting the whole region subjected by the outside region. So it will be H represent the conditional entropy, and for conditional entropy, and then for the second term on the right side of the equation is actually a constant form because phi is the deterministic given X. So that's why we add a C over here. So just we are trying to minimizing the log likelihood of a distribution of phi given a psi. So intuitively, it's very easy to understand. So let's go back to this slide. So in terms of we want to minimizing this one, we just want to maximizing the overlap region. So that's what this derivation is talking about. And then, however, P is something that we don't know. Like we don't know the distribution between. We don't know the distribution between phi and psi, but we can have an upper boundary. So it's borrow the idea from variational distribution. So we approximate it as a Gaussian distribution. So that idea was also similar as the variational autoencoder where we do a reparameterization. So adding the original loss. So the original loss is the downstream loss that's adapted to the new test. Remember, we also need to do a transfer learning on the new test. So we add two of them together. So so this term, the regularization term, is just trying to maximizing the overlapping feature, and then if we minimize the upper boundary, then we could also maximize the mutual information as well. So that's what this equation talk about. However, solving the internal optimization over rho is kind of difficult. So we did a second round of optimization where we borrow the kernel idea, like a kernel learning where we get the phi and psi to represent it into the kernel form, where the x is the input, x prime is also the input from the same mini batch, and then we do a dot product, like transfer the downstream model with the input of X and then do a transfer so that we will get a scalar. So that it is like easier to compute in that way. And finally, the kernel is with respect of the parameter rho. So that's why for the simplicity, we set the rho as a diagonal, like a sigmoid of S. So S is a vector that's randomized. And then we could calculate. So intuitively, we mean that for the rho, we want to know for the model, it can automatically learn itself about which feature from the foundation model is very important. So enough for the math. So let's talk
Boran,
about the
Can I just confirm what is the theta here? What is theta parameterizing here?
Oh, yeah, so I think the so I think the theta over here will will be the will be the so it will be the, so remember I said like we will try to transfer it to a downstream model, so that will be the parameter trainable weight in the downstream model.
Okay, so it will be something like a few additional layers added towards attached to the combined large models that we want to distill.
Not so it's not like that. So sorry for the audience. Like the question being asked is like for the theta for the downstream model. What was the downstream model? So that downstream model will be a whole network. Like will be a small network, like a bird small.
Oh, I see.
Like,
Okay. So
yeah,
here actually we are just distilling to a new model, and the theta is parameterizing that new model.
Right. Yeah.
And what is being used for this distillation? Is it the latent representation or it's a soft label?
Right. So I think it will be the latent representation from the foundation model that's being used.
But if the models have different architectures, how are we going to integrate them into the single small model?
Right. So I think because they have a different architecture and it's on the new test, so we will fine tune on the new test as well. So it will be fine tuned on the scratch, on the like scratch. But then we will also leverage during the fine tuning. We will leverage the feature from the pre-trained model.
Okay. Thanks.
Right. So here are some
question about how you encode the rotation. So it seems that this is a very, very loose approximation, right? We just have a pass-through signal and a diagonal. Do you know how much this will affect the performance?
Right. So I think we try to do like a because that so I think so this one is just to save a computation resource. But when we do the ablation study about the full row like without diagnosis, like it's also similar. Like it's a good so approximation empirically it's a good approximation.
I see.
Right. So, and the next slide will be, I'm just taking a look at the time. So like, so we just tested on the NLP, like we tested on different modality, like the NLP modality, multimodality, and also the image modality. So here shows the results from the NLP front where we tested different sentiment analysis result. And the AFT is our result, is our method. And we combine with other knowledge distillation, B tuning, and also the vanilla one from the original paper, and the like STL means standard transfer learning. And then we find that our method does show a lower error, like a lower error. So the lower the better because we are plotting out the error. And then for the one that we promised before that we want to transfer from different downstream model, so we also transfer from GPT-4. GPT-2 and also Lava. So we just transfer from both model and also Lava chat. And then we plot out the accuracy as well, which is shows in the lower left corner. So we find that our model is scaling up so very well. So the marker means the size of the model. So it ranges from 61 million to 14 billion. So we tested from the different sizes. And then it does scale up very well. The more like we incorporate it, the better it will perform. And then we also tested on the vision entailment, which is a multi-model data set, which work very well. And then this is also the image front. We transfer the Dino VIT giant, which is a 2 billion model, into our small model, which is the VIT into our small model, which is a VIT small, not VIT small. I think it's ResNet 50, and we find that it does also provide a lower error, and then it also scale up well because the vision model usually is very small. The largest it can get is 22B. So we tested up to 2.7B, and then we try to combine the BIT, Dino V2, and then CLIP together. And it shows that the more model we we combine, the better the result it will be. So that's for this side. And then
Boran, just a quick question. So when we distill, are we distilling to a generative model or a particular downstream task model?
Oh, right. So I think for so for this one, we are not distilling it to a generative model. We are just distilling it to a embedding foundation model.
Okay.
Sorry. So the target model is we only tested on the embedding model, but for the pre-train model, we also distill from Lava. Like Lava is also one of our foundation model that we distill from.
So when we evaluate using different task and metrics, we still need to train based on that distill the embeddings, right?
Right.
Okay, thank you.
Right. So, and the last part of the talk, as I expected, we don't have enough time. Just want to briefly go over that we have a model. We have a new model like that's also released online. Using the generative AI to do the weather forecasting. So there are like weather forecasting is also very competitive, but compared with other foundation models such as GraphCast, ClimateX. So our model, which leverage the diffusion model, which could also have the uncertainty estimation that's in nature, because for the diffusion model, the output is also a distribution. And then for the current model, which ignore the domain knowledge, so sometimes it produces a physically impossible result. So just like the recent news about like Aura 2, like it's also violating the physics rule. So that will also, and if you want to change the knowledge, you will also require a pre-training. That's the drawback from the previous setting. And then we have a diffusion model, which is a two-step approach. So we just do, first we do a data-driven forecasting, just as what we did before, and then we do a knowledge alignment. So the knowledge alignment is similar as the RLHF. We get inspired from that. So for the first step, it's a pure data-driven like test. We do it in a supervised way where we have an encoder and decoder. So the encoder and decoder is borrowed from our previous work called the Earth-Former UNet. And then we could do a data-driven. And the second step is we try to align it further with the knowledge itself. And then it could, although it's not a hard constraint, it's a soft constraint. So I know like you probably has some work on the hard constraint optimization that we hope to incorporate in, but so it's similar as like a classifier guidance diffusion model, where we just guided our diffusion model towards the knowledge that we know of. So the knowledge here need to be defined by ourselves. So that's also another drawback that we need to do a follow-up work. So for example, we are setting it to know there is a conservation of energy, or there's intensity drift, like the precipitation. We know that in the future it will average drifting on some direction, so that we can do a prediction in the future. So it's similar as a classifier guidance diffusion model. So we validated on a small data set, because diffusion model is really time consuming to train and to do a prediction. So we just validated on a small region. We hope to scale up more. So it's just like the Aura one, which scale up with the DIT. But so far, this work was done on the last spring, and we find that it does work very well compared with other model. And as I mentioned before, that diffusion model is able to do the uncertainty estimation for the extreme event. So we find that it is able to do like a flood or drought. Like if you want to set at the threshold higher or lower, it is able to provide uncertainty quantification instead of giving one specific value, like the average value for the weather. So
a quick question: what's wrong with the existing physical model?
Right. So I think so the question being asked is what's wrong with the conventional numerical method to do the weather forecasting? There's nothing wrong. So but the problem is it's very computation intensive. So like that's the only thing, because you know, like every country or company is competing for the supercomputing center HPC. So that's what it's used for. It's used for to do the numeric method, the numeric simulation for weather forecast. So for this one, we try to outbid the conventional one. So it's just by doing a few GPU. So a few GPU is considered to be small compared with the numeric simulation that's done by the HPC. So it's, in summarize, we just talk everything about the foundation model from pre-training to in-context learning through RAG, and also maximizing flexibility on transfer learning, and also the social benefit of using the generative AI. So I know that we are running out of time, so I just want to thank first you for inviting me here, and also for all the intern who has done the previous work, especially Yixin, Matthias, Shikai, and Zhihan. That's the work I've been talking about. So it's 1 hour is too short. So I collaborate with like University of Minnesota a lot with George. Bing Kun is also here, and also Jie and Ming Yi. So, and it's also been done. This work is a collection of mine from all the PhD student, faculty member, and also my teammate from AWS as well.
Okay, thank you very much. Questions?
Thank you very much, Boran, for this excellent talk. Can I ask a question regarding the RAG? Yeah, the multimodal RAG.
Yeah, sure. Go ahead.
Okay, go to that slide. So, okay, yeah, just so a couple of questions here. So for the retrieval, we don't train it, right? Are we using a existing embedding model, or we?
Right. So I think we so we are using the existing embedding model. Here we are using the image bind. So it's a pre-trained model from Meta.
Okay. Does it process the text and the image all together, or we need to separate the text and the image?
Oh yeah, that's a very good question. We try to proceed them all together. We try both way, like retrieve separately or retrieve together, because we do want to have a text and image pair together. That will be that will be our example.
Okay, so we need to so we programmatically separate them, and then for each modality input into a particular retrieval, and then when we do the search in the data store, are we also searching based on a per modality basis, or we actually search in a multimodal database?
Oh, right. So we are searching the multimodal database as well. So that's a very good question, because we do want to have a fair comparison for the RAG. The database store is a very important thing that could vary our performance a lot. Like like having a good database is another thread of study. So that's why we try to use the one that we do for pre-training as our data store as well. So we didn't leverage any extra new information. So, but for this work, it can be naturally applied to the data store that's gonna do it so externally as well.
Okay, and the context as the return of the perceiver is actually a multimodal context.
Right. Yeah.
Okay, I see. Thank you. Thank you for your excellent talk.
Other questions? Yes.
Yeah. So yeah, I want to ask a question about like the work that you do, the model distillation, like the transfer learning. So you mentioned that the method is able to kind of leverage like more pre-training models, like distill more pre-training models into like one downstream ones. So first of all, like how do you do that? So do you just add one error terms in that part in the loss function? And then like when you do increase the amount of like pre-training models, do you kind of observe like the performance getting more and more better?
Oh, right. So I think the way we do it is like we just concatenate the feature from the pre-training model together. So if there's only one model, then there will be only one feature. And there's the two models, we will concatenate them together. And then we find that just having more together will be better. It doesn't need to be incorporating them iteratively. So for each dot, we just do another round of training. So whether it's like a one foundation model or two foundation model.
Other questions? For the weather forecasting part, so you have two stages, right? The first stage is it just data-driven approach to solve some PDEs or what? I mean, when people do the simulation, is it that they are trying to solve some PDEs?
Oh, right. So we we are now trying to solve the PDE. It will be just to do it auto-aggressively. So auto-regressively. So meaning that we have the weather information in the past and weather information in the future. So there's no underlying mechanism, just linking the past to the future.
Sure. But is it traditional that people are trying to solve PDE at each time step?
Right.
I see,
Yeah, that's correct.
I see. And so your data-driven approach is kind of equivalent to operator learning to some extent. I mean, the PDE literature, when people talk about, I solved the same PDE many times, and then I use that as data to predict solutions for future cases. Is it similar in style or what?
I think it's hard to tell because
you don't directly use the PDE at all.
Right. So we don't use the PDE at all. But however, we do have another thread of the work which I didn't include. We do have a scientist who's working on the PDE front.
I see.
So her work is trying to sort out of the PDE Navier-Stokes equation, to benchmark the Navier-Stokes.
Because I feel if we do it two-stage, the first stage can still be very, very hungry for data, right? And it's very hard to get enough data, especially geophysically. There are locations where it's hard to collect data, right? Historic data, we don't have enough. It's very sparse. So maybe if you want to incorporate knowledge, I think we should incorporate actually together, right? Instead of doing that two separate stages.
Right. Yeah. So I think we can follow more during the lunch time. I do agree. I think so in terms of to try to make it more efficient, that will fit the title as well. So I guess try to incorporate it from PDE, but how do we learn the PDE? Do we do it learn it through the learn it in the text way or in some other way, or in pin way, so physics informed neural network way, or learn it in the more fashionable LLM way. I know some people are totally against it, learning it through the LLM way. But so I think we can do this.
Okay. And I guess another thing, this is a very high-level question that I'm curious related to the question I asked you about the carbon, the carbon thing, So, every company basically just use their private data and also including the part that get human feedback, right? So it seems to me like these kind of papers where you do comparison of performance is more like commercial publicity instead of because I really don't know what kind of scientific value is there. I mean, I'm just honest. To me, it's more like commercial publicity. So I wonder, what do you think of that? Or how do you convince academic community or scientific community to contribute? If we don't have fair basis of comparison.
Right. So I think so that's the question I've been asking myself too. So that's the question I've been asking myself. So I see pros and cons.
Maybe you should come back to academia.
So I think I see right. So I think I see pros and cons for each way. So as I said, I will prefer the AI for good, AI for social good is something I ultimately prefer. But I also appreciate the compute source that we get because they have all the money, they are working. So they are the for-profit company. But I think the grass is not greener on either side. So, but I do agree that the AI for good is something that excites me the most.
Okay. Any last question before we close? Folks online? Last question? If no, let's thank the speaker again. Thank you very much.
Yeah, thank you for
Thank you very
inviting me.
much. See you next week. Oh, by the way, actually, this Thursday and Friday, we have two ECE,